people spend hundreds of millions on building out large-scale GPU clusters for AI training, AI inference. And yet, when you look at training workloads and we look at the underlying GPU utilization, often these clusters are running at between 30 to 50% in terms of output delivered compared to what the capacity of the cluster is in terms of compute capacity, right? And so really poor efficiency. 30 to 50% efficiency is very poor, and that's really the problem we're addressing. Now, if I peel the onion a bit on sort of exactly what is our vantage point on this problem, if you think about most AI workloads, training being the most extreme, it's arguably the most demanding distributed application that you'll find in history. Specifically, what you achieve by way of training output is dependent on hundreds to thousands to tens of thousands of GPUs working in concert, and ultimately the effectiveness and efficiency of the communication between all of these GPUs dictates how efficient your overall cluster is. And so we really believe that communication is the new Moore's law in AI, and the underlying cluster network and cluster communication dictates how efficiently your overall clusters perform. What takes away from the efficiency and how does that relate to communication? If I were to break down the inefficiency, and I'll translate it quickly to determinism, observability, and sort of how do those things factor in, right? If I were to break down the efficiency problem, the first thing I would say is just sheer availability of your underlying infrastructure. So either because of hardware failures or software failures, you typically find that GPU clusters are available somewhere in the high 80s to low 90s. Now you contrast that with 4 nines of availability in the cloud, and you quickly realize that first, reliability of the underlying cluster is a huge detractor from overall efficiency. And so that's the first problem is when something breaks, whether it's a hardware failure or a software failure, how can I rapidly detect what is causing that failure? Secondly, can I auto remediate against that failure? For example, if a GPU breaks down, can I automatically migrate a training workload from a failed GPU or a failed node to another standby GPU or standby node? That technology is something that Clockwork delivers today, extremely unique. No one is able to have uninterrupted training. And that's an example where observability in terms of rapid detection and then having resilience in terms of failover is critical to raising efficiency. A second example would be, since I mentioned that the overall workload depends on the effectiveness of communication between all of these GPUs, tail latency matters an enormous amount. If you have 1,000 GPUs participating in training and one GPU is running slow because of either a hardware issue that's causing it to be underclocked or because there's a network congestion, that single slow straggler GPU drives down the overall performance of all of the other GPUs in the cluster. So something that we do really well is not just detect that this network bottlenecks, we are able to relieve congestions using software, we are able to load balance communication flows using software, and that allows you to improve the overall performance. So there are 3 core areas in which we differentiate ourselves. Our overall platform is called Fleet IQ. The first one is observability, as we touched on. And the technology underpinning what's unique about Clockwork's approach to observability is that we are able to synchronize thousands of machines in a data center, synchronize the clocks of all of these machines to within tens of nanoseconds of accuracy. Once we synchronize these clocks, what we are able to do then is measure accurately what is the one-way delay of any network packet traveling from any GPU to any other GPU, not just at the network layer, but translating this all the way up through the collective communication library, such as Nickel, all the way up through to PyTorch jobs. And so when we see a job slowdown, we can rapidly translate what is being experienced at the workload level down to what's happening at the net. So that's the first thing. Clock synchronization as a foundation for really insane telemetry is the first building block of the tech company. So the second building block of our technology stack is what we call distributed state transfer. When you're doing training across thousands of GPUs, you're essentially doing collective computation across all of these GPUs. When a failure occurs, it's extremely important to know exactly what is the state of the distributed computation, migrate the state to a spare GPU in a manner where you're preserving this distributed state and restarting all without having the application know that anything's gone wrong. This is extremely unique technology that allows us to deliver seamless training workload failover. And that's the second building block. The third one is really what we call essentially dynamic traffic control. Not only are we able to accurately measure the state of all of your messages and all of your network communication, knowing when congestion is taking place, we are able to transparently reroute traffic within the cluster to relieve congestion, to load balance across different networks, all using software without sort of really caring about whether that's happening on InfiniBand networks or Rocky networks, whether that's Cisco or Arista or Broadcom or AMD GPUs or NVIDIA GPUs. And so those are really, in a nutshell, the three: insane telemetry based on clock sync, dynamically rerouting traffic based on understanding sort of how to reroute traffic across all your networks, and lastly, distributed state transfer to achieve seamless workload failover, if you will.